Our first speaker is Dr. Anthony Broccoli. Dr. Broccoli is Professor of Atmospheric Science and Chair of the Department of Environmental Sciences at Rutgers University, where he also serves as co-director of the Rutgers Climate Institute. His primary interest is in climate dynamics. He has served as co-chief editor of the Journal of Climate, and he's been a contributor and reviewer for the Intergovernmental Panel on Climate Change. Prior to coming to Rutgers, Dr. Broccoli spent 21 years at the National Oceanographic and Atmospheric Administration, Geophysical Fluid Dynamics Laboratory down here in Princeton, and he's a fellow of the American Meteorological Society and the American Association for the Advancement of Science. Without further ado, Dr. Broccoli, and I think your presentation I saw was loaded already, I think on there, and then this is the wireless mic.
Okay. Thank you very much, Jim. I'm just going to get, it's right on the bottom here.
Okay.
Is this, no, we just do this.
Oh, okay, yeah, I was looking, I was like, that's a weird looking.
Yeah.
There we go. All righty.
So thank you very much. I'm going to lead off things today by trying to set the stage and talk a little bit about climate change. I'm sure for many of you, what you hear from me will not be new, but hopefully there'll be enough things in there that maybe you haven't seen in exactly this way before to keep things interesting. So I often like to start talks about climate change with this picture. It's an image taken from a lunar orbiter. That's the moon in the foreground and then the Earth off in the distance. And my purpose in showing this picture is to point out that even from more than 250,000 miles away, you can see the effects of climate when you look at the Earth. You can see the contrast between the tan and brown colors of the Sahara and the green further to the south in Africa and the rainforest regions. You can see the parts of the ocean that have clouds and the parts of the ocean that systematically have less clouds. So climate shapes many things about the environment in which we live. And it's for that purpose that I show this slide, to just make the point that climate is an essential part of our environment. So start off with a little bit of climate change 101 here. We know that fossil fuels represent organic matter that's been buried deep in the earth for a long period of time and turns into gas, oil, coal under pressure and heat. When we burn these fuels, it releases carbon dioxide to the atmosphere. And depending on the type of fossil fuel, there can be differences in the amount of carbon dioxide emitted per unit of energy generated that can vary by as much as a factor of 2, with coal producing much more carbon dioxide per unit of energy generated than natural gas, for instance. And when we tally up all of the emissions of carbon dioxide into the atmosphere from fossil fuel combustion, it amounts to about 32.5 gigatons of carbon dioxide annually, and then deforestation adds about another 3.5 gigatons. Now, I also expressed these quantities in units of gigatons of carbon because in looking at the literature, you'll see the accounting done in both of these different ways. So in terms of gigatons of carbon, it's a nice round number to remember. It's about 10 gigatons per year. And looking at the time series of fossil fuel emissions, I always find it interesting, even though I've shown this slide a lot in my talk, to realize that prior to the middle of the 20th century, most of the fossil fuel burned was coal, and most of the emissions of carbon dioxide were coming from coal. And it was really in the post-World War II period that petroleum became a significant source of fossil fuel CO2, and natural gas has grown also. The other aspect of this time series that I find interesting is that in the 1990s, the emissions from coal had pretty much leveled out. But since the turn of the century, emissions from coal have been rising, and this is in large part a consequence of the rapid economic growth and industrialization taking place in countries like China and India that have vast reserves of coal. Now, as I said, when we combust these fossil fuels, carbon dioxide enters the atmosphere. This is a picture of the Mauna Loa Observatory on the Big Island of Hawaii, where carbon dioxide has been measured since the late 1950s. Here's the time series of atmospheric CO2 at Mauna Loa. These measurements were begun by Professor Charles Keeling of the Scripps Institution of Oceanography. They've since been continued by NOAA, and NOAA has actually set up CO2 monitoring stations all over the world. But this is the record that goes back the farthest. And it shows an increase from about 315 parts per million in the late 1950s to about 410 parts per million today. This time series corresponds almost perfectly to my lifetime. And so one way to put this into context is that over my lifetime, there's been something like a 30% increase in the concentration of carbon dioxide in the atmosphere. Now, we can extend these measurements back further in time by looking at carbon dioxide trapped in air bubbles in ice cores. We can do this primarily from ice cores that have been drilled in Antarctica. The different colored symbols there refer to different places in Antarctica. And they show very clearly that this rise in carbon dioxide is something that's happened since the beginning of the Industrial Revolution. The carbon dioxide concentrations were quite steady around roughly 280 parts per million during the pre-industrial period. So if we extend our record back and compare the current CO2 concentration to pre-industrial concentrations, we've now seen a rise of somewhere between 40 and 45% from pre-industrial. That red line at the end, by the way, is the Mauna Loa record. This time series only extends to 2000. Of course, if we extended it up to the present, we'd be going off the top of the chart into that red band at the top of the slide. Now, why is CO2 important? Again, most of you probably know this. When I give talks like this to my classes here at Rutgers, I often joke that they didn't come to Rutgers, their parents didn't pay tuition so that they could learn that something gets warm when it's in the sun. But that is important in thinking about what maintains the Earth's temperature. The Earth receives energy in the form of visible light primarily from the sun, and that's a heating mechanism. But there's also a cooling mechanism. The warmer an object is, the more energy it emits in the form of infrared radiation or infrared light. And carbon dioxide is important because along with water vapor and some other trace gases, these are greenhouse gases that absorb infrared light, making it more difficult for energy to escape to space. And using simple physical principles, you can do a back-of-the-envelope calculation that shows that if there were no greenhouse gases in the atmosphere, but everything else about the Earth was the same, its surface temperature would be around 0 Fahrenheit, globally average surface temperature. So greenhouse gases make the Earth habitable, but it also stands to reason that if they can make the difference between 0 degrees and the average temperature of the Earth today, which is about 59 degrees, adding more greenhouse gases will have the potential of raising the temperature. And this, of course, is what we've seen when we look at temperatures over the period where we have good records from relatively modern instruments at weather stations. What's plotted here, this is a data set from NASA, are temperatures for each calendar year globally averaged in the black squares. And then the red line shows a smoothed version of these variations, taking out some of the year-to-year variability. The scale on the y-axis is the temperature anomaly, or the temperature relative to some baseline. And in the case of this data set, the baseline has been chosen to be 1951 through 1980. But the choice of the baseline is arbitrary. The graph would look exactly the same if we chose any other baseline. And the main take-home point here is that the Earth's average temperature has warmed by maybe a little bit more than a degree Celsius over this period of time, and that the vast majority of that warming has occurred since 1970. 2016 is that black square closest to the top of the figure, the warmest year so far on record. 2017 was a little bit cooler. 2018 is at present roughly at about the same level, maybe just a tiny bit lower than 2017. Now, why was 2016 so warm? Because in addition to this warming trend, 2016 was an El Nino year when the waters of the eastern Pacific Ocean become unusually warm. Whenever there's an El Nino, the temperatures spike up. The data are currently showing that another El Nino may be developing, perhaps not as strong as the one we had in 2016. And if that's the case, I think there's a very good chance that the 2016 record will be broken in 2019. But again, we don't get caught up too much in how the temperature varies from year to year, because it's really the long-term trend that we're more interested in. Now, these are temperature records from modern weather stations. Obviously, we'd like to place this warming in a larger context to know what was happening before we had enough weather stations with modern instruments to determine the global temperature in the way that it's been done here. So one way to do that is to try to use various natural archives, including tree rings, ice cores, corals, things like historical records of when rivers and lakes froze, cherry blossom blooming dates from Japan. All of these natural archives can be used to reconstruct global temperature. These reconstructions are not as accurate as measurements from modern thermometers. So as you can see in this graph, each of the colored lines is a different reconstruction. They don't agree with one another perfectly. Several of them have uncertainty bands around them in lighter versions of their color to indicate what some of the uncertainties are in these measurements. But when we look at this in a 1,000-year context, we can see again that just as the changes in carbon dioxide that we've seen are unusual, the changes in temperature we've seen are unusual. There's evidence that there was a gradual, slow cooling trend from about the start of this record through the early 19th century. But again, with industrialization and the rise in CO2, temperatures started to rise, and the increase in temperature that we saw during the 20th century and since that time is highly unusual, even in the context of the last 1,000 years. Now, that's a global perspective. I'd like to use New Jersey as an example to show that many of these effects are being felt locally as well. And so over the next few minutes, I'll intersperse some data about New Jersey in with information about more global changes. So the temperature time series for New Jersey shows a long-term upward trend of just under 3 degrees per 100 years. As with global temperatures, we've seen more rapid warming in recent decades. The 7 warmest years have all occurred since 1998, and for New Jersey, 2012 was the warmest year on record. Now, of course, when we're looking at New Jersey, we're looking at a relatively small region, so the variability in temperature from year to year is much larger for a small region like New Jersey than it is globally. And one thing that's important to keep in mind is just because we have a cold winter or a cold year, that's not telling us very much about the long-term trend. We really have to step back and look at things in a broader context. So if you focus your attention on the right-hand side of the diagram, you'll notice that for the past 20 years or so, the temperature every year has been above that horizontal line. That horizontal line is the average temperature for the 20th century. So even a cool year relative to the last 20 years is warmer than what the average temperature was for the 20th century. So it's really important to think about this longer-term context and not just how the temperature of a particular year or a particular season compares to what has happened recently. Now, this is a diagram based on one that was originally put together by our state climatologist, Dave Robinson, my Rutgers colleague, and Jeff Huffman from NJDEP. And what you see here is a set of boxes, each one of which represents an individual month, starting in January 2000. So the years run along the horizontal axis, the months run on the vertical axis. And for each month, we have colored in a box if that month was one of the 5 warmest months for that time of year, in other words, 5 warmest Januaries, Februaries, etc. And we've colored the boxes blue if it was one of the 5 coldest months. You'll notice there isn't any blue. That's not a mistake. It's not a problem with the projector. It's not a problem with your color vision. Because since 2000, we've had 40 unusually warm months out of a possible 60, maybe plus a couple more if there are ties. 40 unusually warm months and 0 unusually cold months. In 2018 alone, 4 months, February, May, August, and September, have been among the 5 warmest for that time of year. So we are certainly seeing the effects of this warming in its implications for unusual or extreme temperatures here in New Jersey. There are other aspects of climate change that our records show are happening as well. This is a bit of a complicated metric to describe. You can read the headline there at the beginning, but essentially it's telling us what fraction of the area in the northeastern United States has had unusually heavy precipitation. And again, it's a year-by-year time series. Each of the bars corresponds to a particular year. And there's a smooth version of the time series in red. But what's clear is that over the last couple of decades, we've seen an unusually high frequency of these intense rain events. And this is something that our models that we use to simulate climate change told us would happen, that the heaviest rain events would become heavier. And we've been seeing this in observations not only in the northeastern United States, but in many places around the world. Sea level is another aspect of climate that has been changing. Over the globe, the century scale trends in sea level have been a rise of just under 2 millimeters per year. But this rate has nearly doubled during the past 2 decades. In New Jersey, the sea level rise has been more rapid. These are from tide gauges at Atlantic City and Cape May. And in New Jersey, the rise has been about 4 millimeters per year. And that's happening because at the same time that sea level is going up, the land is sinking here in New Jersey. Some of that is the geological legacy of the last ice age, the Earth's crust slowly going back to where it was before it had these big, heavy ice sheets sitting on them, as they were until about 10,000 years ago. But some of it is also because coastal sediments are becoming compacted, part of that for natural reasons, part of it perhaps also because of extraction of groundwater from those coastal sediments. So whatever sea level rise happens globally, it will happen more rapidly here in New Jersey because of the subsiding land. And that tendency for subsiding land is a characteristic of the entire mid-Atlantic region, which is also why places like the Norfolk area are experiencing more rapid sea level rise than the global statistics would indicate. What will happen in the future? So now going back to a global perspective. These are projections of temperature for two different scenarios of greenhouse gas emissions. The low emission scenario, which is the green line in the figure on the upper left, is one in which rapid limitations on emissions are imposed so that emissions peak around the middle of the 21st century and then decline thereafter. The temperature changes associated with that are shown by the blue line and the blue band in the figure on the upper right, which would indicate that in response to that scenario, there might be an additional degree Celsius or so of warming by the end of the 21st century. A business as usual scenario is represented by the blue line in the curve on the upper left, so that leads to CO2 concentrations of nearly 1,000 parts per million by the end of the century, which would produce warming of about 4 degrees Celsius. The two maps at the bottom show the temperature changes in the last few decades of the 21st century relative to a late 20th century baseline from the low emission scenario on the left and the high emission scenario on the right. And an important take-home message is that the global warming simulated by our models is not expected to be uniform. In fact, the warming that we've seen over the course of the last century has not been uniform. The Arctic has warmed extremely rapidly, as have parts of the high latitude northern hemisphere continents. The land warms more rapidly than the ocean. And some of the slowest warming places are the waters around Antarctica and this patch in the North Atlantic Ocean. The slow warming there is associated with a slowdown in the Gulf Stream circulation. So what happens in the future crucially depends on the emissions between now and the end of the century. So now looking again at some specific impacts, heat waves. These maps show projected increases in the number of days over 90 degrees Fahrenheit here in the northeastern quadrant of the United States. So again, using New Jersey as an example, here in central New Jersey, a late 20th century average is maybe around 15 to 20 days above 90. Under a high emission scenario, that number could rise as high as 40 or 45 days. And there would certainly be quite a number of 100-degree days happening there as well. Lower emission scenario, still some increase, but the increase is not as dramatic as it is for the high emission scenario. Those heavy rainfall events that I was talking about, here's a scene from a few miles away from here, Blackwell's Mills, New Jersey, during Hurricane Irene in 2011. Heavy rains are expected to become heavier. This is an interesting map because what's been done here is to analyze the output from a lot of different climate models for the high emission scenario for a period towards the end of the 21st century, and to ask the question, if you just look at the 5 wettest days during the year, how much wetter will those 5 days become? And what's fascinating about this picture is that almost everywhere the heaviest rains are expected to become heavier. Now, if you looked at the average precipitation, the average precipitation would go up globally, but a map of changes in average precipitation would show places that get wetter and places that get drier. But almost everywhere, just a few exceptions, you can see just maybe a few small patches of those warmer colors, just about everywhere the heaviest rains are expected to become heavier. And finally, a little bit about sea level. This is a picture from one of the towns on the Barrier Islands here in New Jersey. This isn't Hurricane Sandy or anything nearly as dramatic as that. This is just a maybe slightly stronger than average winter storm. What you're looking at is normally a street but it's covered with maybe a foot or so of water from Barnegat Bay, which is shown there in the background. Projections for sea level in New Jersey, as I said before, indicate a more rapid rise than the global rise. And that's because the land is sinking, and also because there are projected changes in ocean currents that would add to the rate of sea level rise near the New Jersey coast. Now, we had a group of scientists led by my colleague Bob Kopp here at Rutgers that was brought together by the New Jersey Climate Adaptation Alliance. And they put out a report indicating that by 2030, sea level along the New Jersey coast will rise between 0.6 of a foot and 1 foot relative to the year 2000. By 2050, best estimate goes up to about 1.4 with a range of 1 to 1.8. By 2100, the amount of sea level rise depends on future emissions. It actually doesn't depend on future emissions very much over the next several decades. So under a high emission scenario, the best estimate is about 3.5 feet with a range of anywhere from 2.4 to 4.5 feet. And I might point out that that's the likely range. That means there's roughly a 2/3 chance that the actual sea level rise would fall within that range. Higher sea level rises are very possible if Greenland and Antarctica melt more rapidly than we expect them to. And that's a subject of a great deal of research right now to try to understand how those large ice sheets are responding to changes in climate. So anyway, I'm going to conclude by just reviewing for you the options we have for dealing with climate change. Mitigation refers to efforts to reduce or prevent the emission of greenhouse gases into the atmosphere. Adaptation means planning for changes in climate that are expected to occur, primarily by taking actions that make the impacts of climate change less severe. And then geoengineering is a very controversial idea that I'm sure many of you have heard about, that involves trying to deliberately do something else to the large-scale planetary environment in order to counteract the effects of human-caused climate change. This could be making clouds brighter or putting sulfur dioxide into the stratosphere to reflect sunlight, or even putting tiny little reflectors into space to reduce the amount of sunlight reaching the Earth. Geoengineering is very controversial, many concerns about feasibility and unexpected, unintended consequences. So you won't hear much about geoengineering, if at all, today, but you will hear a lot about mitigation and adaptation, very practical ways that we can try to address this problem of climate change. So thank you very much for giving me this opportunity to speak this morning. And Jim, if we have a minute or two, I'd be happy to take a couple of questions. Yes?
How do you explain some of the climate change skeptics that say that the temperature change is cyclical? Because the data, as you have presented, is pretty clear that over the long duration, it's not cyclical. Mm-hmm. So can you give me some arguments to maybe, when these arguments do come up with folks that I'm talking to, that I can, speak about it a little bit more intelligently?
Sure. At first I was worried because I thought you were going to ask me to justify the arguments that are being made by the climate change skeptics, which would really be impossible. But no, there are variations in climate that are cyclical. The ice ages were an example of this. When we look back at the last several million years, there have been periods where the ice sheets grew to cover the northern half of North America, and then times when they've retreated to where they are now in just Greenland and Antarctica. But we understand why those cyclical changes occurred. They occurred because there are slow changes in the shape of the Earth's orbit and the tilt of the Earth's axis that have much less of an effect on the total amount of energy that the Earth receives than putting carbon dioxide in the atmosphere does. Basically, there was a very good op-ed in the New York Times yesterday by Gavin Schmidt, the director of the NASA Goddard Institute for Space Studies in New York. And he basically made the analogy that those of us who study climate dynamics are like climate detectives. We see that warming has taken place, and we're trying to figure out what the cause of that warming has been. And so, like a detective in solving a crime, you might have many suspects, but you can eliminate many of those suspects. The sun hasn't gotten brighter. And had the sun gotten brighter, we wouldn't be seeing cooling in the stratosphere at the same time we're seeing warming in the troposphere. We don't see any other plausible mechanisms to cause this change in climate. And one of the things I would point out is that rather than taking comfort in the fact that climate has changed in the past, as if that somehow means we can't be causing any of the changes that are happening now, what that really tells us is that our climate system is very sensitive and that it doesn't take much to change the Earth's climate. Putting enough greenhouse gases in the atmosphere to essentially cause an extra 2.5 watts per square meter of warming is a big deal compared to the changes that led to the ice ages. So we've eliminated the other suspects. This isn't just part of some natural cycle. As you saw in the data, the temperatures didn't show any warmings like this over the past 1,000 years. So I don't think that's something we can really take any comfort from.
I just have one quick question.
Sure, Jim.
I guess people refer to it as the Keeling curve. You see the sort of cyclical nature, and it seems fairly uniform, and you get this.
Yes.
What causes that cyclical nature in that diagram?
Yeah, that's the effect of vegetation. Most of the plants in the world are in the northern hemisphere. So when they're growing in spring and summer, they're taking carbon dioxide out of the atmosphere and through photosynthesis using that to build biomass. So when that happens, the amount of carbon dioxide in the atmosphere goes down. And then in the fall and winter, when leaves fall off the trees and decompose and carbon dioxide is returned to the atmosphere, the carbon dioxide starts to go up again. What we actually find now that NOAA has measurements all over the world is that if you look at measurements from the South Pole, you don't see that cycle because the vegetation that produces it is very far away. And if you look at measurements from, say, Point Barrow in Alaska, you see an even larger cycle than shows up at Mauna Loa. But that's northern hemisphere vegetation. Yeah. Thank you very much.